All right, let's jump right in. Think about this for a second. What could possibly connect a powerful antibiotic with the hormone that keeps your body running? Well, it turns out there's a hidden chemical language, a kind of molecular blueprint that has totally shaped our modern world. Today, we're going to decode the secrets of haloalkanes and haloarenes.
And when I say they've shaped our world, I am not kidding. Just look at this list. We're talking about chloramphenicol, a drug that fights deadly typhoid fever, or chloroquine, which is so crucial for treating malaria. Halothane, an anesthetic that makes modern surgery possible. Even our own bodies get in on the action with the thyroxine hormone. These compounds are literally everywhere, working behind the scenes in plain sight. So that leads to the big question, right? What is the one simple yet incredibly powerful chemical feature that links all of these amazing substances together? What's the secret sauce?
Well, the answer starts with something I like to call the great hydrogen swap. It's this one fundamental move in chemistry that opens up a whole new universe of molecules, each with some pretty extraordinary abilities.
And here it is. At its heart, it is beautifully simple. You take a basic hydrocarbon, just a molecule of hydrogen and carbon, and you literally swap out one of its hydrogen atoms for a halogen atom. That could be fluorine, chlorine, bromine, or iodine. That one little trade, it changes everything.
Now, this one simple swap creates two major families. On one side, you've got haloalkanes. That's where the halogen latches onto what's basically a simple chain of carbon atoms. On the other side, you have haloarenes, where the halogen attaches directly to a super stable aromatic ring. So if you want to boil it down, the big difference is just a chain versus a ring.
Okay, so you can imagine this creates a ton of new molecules. To make any sense of it all, chemists need a system. And the first, most logical way to start organizing things is just to count.
Yep, it starts that simple. If the molecule has just one halogen atom swapped in, we call it a monohalo compound. If it has two, it becomes a dihalo compound. And if you've got three or more in there, now you're talking about a polyhalo compound. It's the first step to bring some order to this huge new molecular family.
But here's the thing. Just counting the halogens doesn't really tell you how these molecules are going to act. To do that, we have to dig a little deeper. We need to look at the exact carbon that the halogen is connected to. And this is where the classification gets way more powerful.
So, to really get a handle on the chemistry, we're going to zoom in. We'll focus on those monohalo compounds. Remember, the ones with just one halogen. And specifically where that halogen is bonded to a certain type of carbon, called an sp3 hybridized carbon. Trust me, this is where all the interesting variety comes from.
All right, first up is the primary alkyl halide. So you look at the carbon that's holding onto our halogen. If that carbon is only connected to one other carbon atom, we call it primary, or 1 degree. Think of it like it's sitting right at the end of a carbon chain.
Okay, so what if that carbon holding the halogen is connected to two other carbons? Well, you guessed it, that makes it a secondary, or 2-degree alkyl halide. This one isn't at the end of the line. It's sitting somewhere in the middle of the chain.
And finally, we've got the tertiary, or 3-degree alkyl halide. In this case, the carbon with our halogen is like a central hub, connected to 3 other carbons. It's sitting right at a branch in the road. And knowing the difference between primary, secondary, and tertiary is absolutely crucial for predicting what these molecules will do.
Okay, so that all makes sense. Primary, secondary, tertiary. But, chemistry always likes to throw in a few curveballs, right? What happens if that special carbon, the one holding our halogen, is sitting next to something a little more interesting, like a double bond or one of those aromatic rings?
Well, that gives us two more really important categories. If our special carbon is right next door to a carbon-carbon double bond, we call that an allylic halide. But if that same carbon is neighbors with a full aromatic ring, then we've got ourselves a benzylic halide. See? The neighborhood that carbon lives in changes the whole story.
So we've thrown around all these names and categories: primary, secondary, allylic, benzylic. And you might be thinking, why all the complicated labels? Well, because this isn't just about memorizing vocabulary. This is the actual blueprint that chemists use to build the world around us.
So here's how it all snaps together. By knowing if a halide is an alkyl, allylic, or benzylic type, a chemist can predict how stable it is, how it's going to react, and what incredible new molecules they can build from it. This whole classification system is the key that unlocks a molecule's true potential.
And that right there is the big takeaway. This quote really says it all. This system isn't just some exercise for a textbook. These molecules are the fundamental starting materials, the absolute essential building blocks that chemists use to create countless other compounds that we all depend on every single day. Which brings us right back to where we started. From life-saving medicines to the very chemistry inside of us, this molecular blueprint has already changed the world in ways we can't even imagine. So the only real question left is, with this powerful language of chemistry at our fingertips, what will it build next?